right. Well, good morning, good afternoon, good evening, folks, wherever you are. Thank you so much for coming to join us for another hopefully fantastic PalaeoPERCS talk. We're really excited to have you with us this week. So this week, our PalaeoPERCS speaker will be Agathe Toumoulin, who's going to talk to us about evolution of temperature seasonality from the mid-Eocene to the early Oligocene, a model data journey. So I will just start out by going over the format of today's seminar, which will be quite similar to previous seminars if you've been able to join us in the past. So I'll start out with a short welcome and some announcements, which is what you're hearing me do right now. And then we will move into Agathe's talk. And we will follow that up with a moderated Q&A session with her. After the Q&A session, we will move into sort of an after-talk informal tea time where we'll have a chance to talk a little bit more one-on-one as a group. And at any point during the seminar, please send any questions that you have via chat to our questions host, and those will be relayed to Agathe at the end of her talk. Oops. So I'm so sorry. I think that I'm missing a little bit of a slide here, so you'll just have to hear me say this verbally. So PalaeoPERCS seminars really value the participation of all people interested in the paleosciences, and as a part of that, we do ask that all participants sign and abide by our code of conduct. So if you have managed to get into today's seminar today without having signed our code of conduct and joined our mailing list, we would ask that you take just a moment to go to our website, which is PalaeoPERCS.com, and read through that code of conduct and make sure that you're able to abide by that. Over the course of the seminar here, you should not be able to unmute yourself. However, if you find that you are able to, we ask that you just remain muted for the duration of the seminar. And finally, we ask that as you have questions during the talk, you send those questions via chat to the questions at PalaeoPERCS host, who's Chrissy today, and those questions will be relayed at the end of the talk. Similarly, if you run into any questions for the PalaeoPERCS committee or any technical issues during the talk, please also send those to questions at PalaeoPERCS host, and we will help you the best we can. So with that, I can now introduce Agathe. She did her bachelor's at the University of Toulouse and a master's at the University of Montpellier, and then her PhD at CEREGE. She is currently working to construct an amazing postdoc project that will be carried out shortly in Germany. And so with that, I think I can pass over the screen share as well as the virtual stage here to Agathe.
Thank you very much, Katie. Okay, can you see it well?
Looks great.
Perfect. Okay, hello everybody. Thank you very much for being here today. I'm really happy and thank you for this introduction. I'm really happy to show you the last results of my PhD work, which generally aimed at better understanding the evolution of temperature seasonality through the greenhouse ice-house transition from the mid-Eocene to the early Oligocene. The results I'll show you today are part of a study that was recently accepted as a preprint in Climate of the Past discussion and that you can find online under this slightly different title. It was made possible thanks to close collaboration with the nice people you can see here, that are Delphine Tardif, Yannick Donadieu, Alexis Licht, Jean-Baptiste Ladan, Lutz Kunzmann, and Guillaume Dupont-Nivet. I will make a close talk at EGU this year, and you can find it in this climate session. It was made possible thanks to the Tilly Edgar Journal Grant. So, to start with a little pinch of general context, you probably all know that, or most of you know, that the Eocene is a key period in the history of the climate evolution through the Cenozoic. And it's generally known as the last greenhouse period with generally higher surface temperature, apparently low equator to pole gradient, a widely spread tropical biome, and poor amount of land ice. The climate generally cold and enabled around the Eocene-Oligocene transition a major expansion during the Eocene-Oligocene transition, near the Eocene-Oligocene boundary, a major expansion of the Antarctic ice sheet. But when we learn every day more from benthic and from ocean proxies and what happened through the ocean realm, there are still an important question concerning what happened on land. We know that some important biodiversity crises have been described, notably in Asia with the Mongolian remodeling and in Europe with the so-called Grande Coupure that was described more than a century ago. And these events have been associated either to climate deterioration or to migration and competition process. At a global scale, the vegetation from the mid-Eocene to the late Eocene and after through the Eocene-Oligocene transition have been described as rather heterogeneous, with on the one hand some areas where the vegetation appeared to be rather stable through time, notably in Central Europe and South America. But on the other hand, some places where the tropical or paratropical vegetation shift to more temperate vegetation with the increase of the proportion of deciduous species and cold tolerant species. And based on this observation, some authors have been suggesting that the Eocene-Oligocene cooling may have been particularly marked through winter, a decrease of winter temperatures. And this would have had a huge consequence on what we call the seasonality of temperature, which may be represented by a mean annual range of temperatures, which is simply the difference between summer and winter temperatures. We can see from this simple scheme then that when we only cool winter temperatures, then we increase this range of temperatures, so what we can call seasonality. We may also increase the range of temperatures by warming more summer temperatures than winter temperatures, but this is a bit out of the scope of the global cooling of the Eocene. And there's only a few number of modeling studies that have been focusing on the land climate of the time, and a very few number, actually only one species, that have focused on the intra-annual variability of these terrestrial climates. It's the study of Agathe and collaborator in 2009 that is actually a palynological study with some elements of climate modeling inside that explained that with a PCO2 lowering from the Eocene to the Oligocene, the temperatures decrease in the northern hemisphere, but more importantly during winter, which through albedo feedback provoke a more important decrease of winter temperatures. But this study only focused on the northern hemisphere and on the effect of PCO2 lowering, and we may wonder, what about the rest of the world and what about the other climate forcing? So our approach for this study, I'm going to introduce you. It was first to compile all the data talking about seasonality change through this period of time, so from the mid-Eocene to the early Oligocene, and then to try to model the seasonality change on land in response to PCO2 drop, but also Antarctic ice sheet formation, and another parameter which is barely never represented, and is the related sea level lowering. We won't talk about obliquity in this presentation, because although it's a very important parameter to consider when we talk about seasonality, our study focused on long-term change that are not sensitive to this parameter. In addition, although rainfall seasonality is also an important parameter. This was a bit out of the scope of the study, and I highly encourage other people to continue and doing the same thing with this, but we won't talk about it here. So the first step of this study was describing where and when were people documenting seasonality change. Most of the data we combined were from the paleobotanical record and came from two methods that are named the coexistence approach and the CLAMP. Coexistence approach is a method using the ecological niche of fossil species relative, and CLAMP, it means Climate Leaf Analysis Multivariate Program, is a method based on functional approach which uses the evolution of fossil leaves physiognomy. That means fossil leaf size and shape. Both these methods provide an estimate of the warmest and coldest month mean temperatures, summer and winter temperatures that may be help calculating this mean annual range of temperatures pretty easily. We also combined some stable isotopes data, notably from the oxygen and cloud isotopes. For some species, observing an increase in the temperature, an increase in the variability of their temperature prediction that they were interpreting as an increase of the temperature seasonality. Finally, our study also contained some qualitative data, as for instance, this study from Lee and collaborator, which observed the appearance of the Nelumbo species with suburbs, and that they interpret as the onset of a cold winter. We either get the mean annual range of temperatures from the study when it was a metric available, or calculated it from the raw data given by the study, by being precautious and trying to respect the original interpretation of the study, of course. So all the data we have are visible on this map, and the use of different symbols here reflects the fact that we selected the data depending on their availability. And so all the points you can see represent a record of seasonality evolution between two time steps, either from the mid-Eocene to the late Eocene, or from the mid or late Eocene to the early Oligocene. We used the general circulation model IPSL CM5A2 to simulate the temperature seasonality over the world. And this tool is a nerve system model that is being developed at the Institut Pierre-Simon Laplace. It's particularly suited for paleoclimate reconstruction since it enables the run of long simulation that is a requirement to study mid-time climate. It also got a quite good resolution for our model. And with this tool, we made both middle, late Eocene and early Oligocene simulations. We ensured the simulation were stable by looking at intermediate and deep ocean temperatures through time. All simulations were run for 4,000 years. So our middle-late Eocene was made with an intermediate PCO2 of concentration of 840 ppm. When we compare this value to the recent data compilation for the PCO2 evolution over the Cenozoic of Foster and collaborator 2017, we see that it's rather in the middle of prediction for the middle-late Eocene. And because of this high concentration, we do not have ice on land. Our simulation uses a paleogeography of 40 million years that you can see here, and that was recently published by Poblete and collaborator in this year. We used an Eocene solar constant and modern orbital parameters. We also made a warmer Eocene simulation with 4 times the pre-industrial level of CO2 because this higher value is generally the one that is used by climate model to better represent the sea surface temperature estimation made by proxy for the Bartonian and Pre-Ebonian. But since our study focused on the difference between late Eocene and early Oligocene temperature seasonality, using this 4 times the pre-industrial level of CO2 simulation provoke 2 strong temperature difference across the UT, and then was not realistic. So I won't talk about this other simulation here, but I have additional diagnostic at the end of the presentation if you want to know more about, and you can of course also check for our preprints in Climate of the Past discussion. We then made an early Oligocene simulation with a lower PCO2 concentration of 2 times the pre-industrial level of CO2, 2x. Please note that in all my talk I'll use 3x to define or 2x to define the concentration of CO2. It's important to remember. And to represent well the Oligocene, we also add a continental scale Antarctica sheet over Antarctica. This volume of ice comes from another study from Ladon and collaborator in 2014 and was modeled especially for this atmospheric concentration of CO2. And to represent the indirect effect of this glaciation, we also apply a modification of the sea level homogeneously. There's a minus 70 decrease of the sea level between this simulation and the Eocene one. I'll show you later that it provokes some geographical change that are important to represent the Rupelian. In addition, so to this 3 times the pre-industrial 3x simulation and 2x ice sea level simulation, we also made 2 theoretical simulations to better understand the effect of CO2 change or ice cover change or sea level change that are a simulation with only 2 times 2x PCO2 but no ice, and one that has this PCO2, an Antarctic ice sheet, but no sea level adjustment. So let's now move a bit to the results. So here is our first map showing the effect of the PCO2 lowering of 1x, so 280 ppm, on the Eocene temperature seasonality. Here I'll name delta MATR, the difference in seasonality, either between 2 simulations or 2 proxy estimates, if it comes from the data. What we can see is that the PCO2 lowering provoke both zones of increasing seasonality, that are these zones in red, and zones of decreasing seasonality that you can see in blue. On this map, there are our data points that I introduced you a few minutes ago, and the orange points represent data points of increasing seasonality, but from the qualitative record that cannot be directly attributed to a numerical value. Seasonality increased zones may be explained by more important cooling during winter. And this is visible on the map. You can see on the right side of the screen that shows the amplitude of the cooling through this 280 ppm PCO2 lowering, either for January, February, and March at the top, or for July, August, September at the bottom. And you can see the cooling is fairly more pronounced in winter. This results simply from albedo change, because at lower PCO2 we got a more important sea ice fraction over the Arctic Ocean, and also more snow accumulation on high latitude continents. This increases surface albedo, especially in January, February, March, as compared to July, August, September at lower PCO2. This result was totally expected. It is what the study of Elfret and collaborator in 2009 described. and it's generally called polar amplification. The zones of decreasing seasonality are conversely associated to more important cooling in summer. And as you see, it is the result of several mechanisms. First, there are some important change in precipitation and evaporation patterns. On this side, you can see a map showing the net precipitation in July, August, September for the Eocene simulation. Net precipitation are simply the difference between precipitation and evaporation in a given area. We all know, or it's becoming fairly common, that in the modern context of climate change, the wet zone should get wetter and the dry zone should get drier. Here, with a reduction of the PCO2, we observe the opposite. And this is what this map shows you. It shows the difference in net precipitation when we lower the PCO2. We see that these wet zones tend to get drier, and oppositely, the dry zone tend to get wetter. And this more important input of water in the dry zones will have an impact on the latent heat fluxes. It means that the soil are getting more wet in summer, and then there's more evaporation and more latent heat flux, and so there's a more important cooling in summer in these decreasing seasonality zones that are contoured in red in magenta. This change in precipitation and evaporation will have a direct impact on the low cloud cover. Low cloud, so it's low altitude cloud, are these fluffy and thick white cloud, and they have a very high albedo effect. They tend to have a cooling impact on the surface temperatures. And we can see from the map here that when the PCO2 lowers, there's a general increase of the clouds over mid-latitude, but that this increase is more pronounced in the summer of both hemispheres. So this will have a direct effect on the temperatures below, and this cooling will be transferred to land. Here is a zoom by winds, and thus will have an effect of decreasing the temperature seasonality decreasing the temperature seasonality, notably in Patagonia and Europe. Last feedback related to PCO2 drop is a concern the Arctic sea ice, but we saw together that it increases albedo during winter and then favor winter cooling, but it also limits the exchange between the ocean and the atmosphere, especially during winter. And by limiting the exchange between ocean and the atmosphere, it will also limit the cooling of ocean surface temperatures. And that's what you can see from this plot. We see that actually, when we look at the sea surface temperatures of the Atlantic Ocean, the decrease of temperature is more pronounced in July, August, September as compared to January, February, March. And this difference is visible until at least 20 degrees north, so it concerns a big part of the Atlantic Ocean, and this had an impact on Europe. When we now take a look more precisely at the agreement of this seasonality change we model and what the proxies say, we see that there's no obvious agreement at all when we compare to the simulation, so just 2x and 3x simulation. But that's not really surprising, since we do not expect being able to reproduce the seasonality change through the Eocene Oligocene transition without taking into account change in Antarctic ice sheet extent. But it's also important to note that the agreement of this simulation with only the Lutetian to pre-Ebonian change, so mid to late Eocene seasonality change, is not really better, but it also could be because we don't have much point for this period of time. When we now look at the effect of the Antarctic ice sheet alone, so without changing the sea level, we observe a very strong signal over southern latitude, and especially over Antarctica, with a strong reduction of the temperature seasonality. And here it is also linked to albedo, the change in surface albedo. We might be surprised that the effect we observe here is the opposite of what we just saw for the Arctic Ocean and sea ice expansion, but it's actually pretty easy. So if we go back to the north and talk about sea ice, we may say that by lowering the PCO2, we allow the formation of large-scale sea ice over the Arctic, which tend to increase the albedo variability over the year. And this increase in the albedo variability increases also temperature seasonality. For Antarctica and southern latitude, when we add an ice sheet over Antarctica, then the soil is all year round white. So we decrease this albedo variability, which tend to have a negative impact on the seasonality of temperatures. The picture we get when we now look only at the effect of the sea level is totally different. And it's very interesting to see that this indirect consequence of the Antarctic ice sheet is visible all over the world. Actually, by lowering homogeneously the sea level, we turn some ocean area into land area, and all these newly land area are those that are shaded in gray on this map. This map is our 40 million years map with this sea level lowering. So we can see that there are some very important changes, like the Turkish Sea drought, the Protoparathes retreat, and the Arabic Peninsula emergence that will totally change also some water flux. And because land have a lower thermal inertia than ocean, then we will have a strong increase of temperature seasonality in these zones. When we combine now all four things together, so PCO2, Antarctic ice sheet, and its sea level lowering, we obtain this map that may be interpreted as what we would expect for seasonality change through a whole greenhouse ice-house transition from the mid or late Eocene to the early Oligocene. What we can see is that the agreement with data points is far better. And we still have a slight difference between proxies and model of 3.3 degrees. This difference is actually pretty well explained by the fact we predict the presence of some decreasing seasonality zones in areas where the data show no change in temperature seasonality. We may not say that there's a good match between our prediction and what the data say here, but it's still very, I think it's important to notice that we do not predict seasonality increase in this area. And we may wonder if this mismatch could be a recording problem. Actually, was it easy for plants? Is it possible to record a seasonality lowering in an already polyseasonal world, especially if this lowering seasonality are characterized by summer cooling? I'm not sure whether or not it could be such a bias. A nice result also that I was not expecting at all is this one. By combining all four things together, we observed a better agreement with some points showing a seasonality change between the mid-Eocene and the late Eocene. That are these triangles you can see, as for instance in Kamchatka and South China. Of course, we do not aim at we can't pretend representing a mid-Eocene to late Eocene seasonality change using this 70-meter sea level drop, since it corresponds to the major Antarctic expansion, ice sheet expansion. But it suggests that maybe some before the transition Antarctic ice sheet fluctuation and sea level lowering, as it has been described during the late Eocene, could explain the seasonality increase we observe in this coastal area. Well, if we want now to summarize a bit this all and to replace this in a more precise paleo context, we may say that the greenhouse ice house transition started with carbon cycle perturbation, maybe with a CO2 decrease. That results that may have an impact on high latitude, either in the northern hemisphere or in the southern hemisphere, and may have provoked the earliest change in seasonality. This was hypothesized by the study of Zenadi and collaborator in 2007, but they didn't have the data to confirm this idea. We think it's possible with this PCO2 forcing, and this is also what described Eldred and collaborator in 2009. But we need more data in this area to really show the earliest seasonality change well before the Eocene-Oligocene transition there. Then, along with this global cooling and early fluctuation of the Antarctic ice sheet, some change would have occurred in coastal areas, notably in the West Pacific. But it's only with this major expansion of the Antarctic ice sheet during the early Oligocene that we really observed some change in the seasonality of mid-latitude. Question that seems important to me is, may this seasonality change have had an impact on the Eocene-Oligocene transition biotic crisis? It's not a question we may answer with our model, but we may still provide new elements to consider the evolution of biodiversity at a global scale. Maybe also the seasonality strengthening we will construct in Asia contributed to this Mongolian remodeling. And what question that seems important also is, are the presence of these decreasing seasonality zones, so these zones where there were no special cooling, an explanation for the reason we do not observe important change in biodiversity in these areas. There's of course many other things to do that could be done to go further. And the first one would probably be using a realistic riparian paleogeography. As I told you, this geography, that is the one here, is our 40 million year paleogeography modified by unhomogeneous sea level lowering. And there are some tectonic events that are not visible or taken into account, as for instance the northward migration of Australia and India, and that could enhance the predictability of seasonality change to use a proper Riparian map. We could also consider do the same analysis using seasonality, rainfall seasonality proxies and just modeling the seasonality of rainfall to better understand and describe the thread that could have been in place during this period of time. And finally, our study was based on proxies documenting seasonality change through from the mid-Eocene to the early Oligocene. And we may also work on all the palynological data that are available to reinterpret, to just look at this data again and try to figure out what they may say concerning the seasonality to have more point and a more precise picture of the seasonality change documented by the proxy. Thank you very much.
Hey, thank you so much for that really fascinating talk. That was really wonderful.